Okay, well, we're not going to do a lot today. We didn't do a lot last time. We're not going to do a lot today because we have this other class member who's taking the course distance style, and I have to get her caught up. So we're just going to finish this section, and I might wave my hands and talk a little bit about the next section. But until I have everything posted and have all the material so that she can access it, we really don't want to get ahead. So what I'm going to do is a few examples. And this one, this is number 8, page 22, was one I was originally going to assign. And then I got to working it and got down to part C and decided that was too hard. But then the other day, I went back to look at it and said, wait a minute, that's not hard at all. So I should have assigned this one. But what we're looking at here is we have a point moving along a number line. And its derivative at time t, its derivative with respect to t, is t cubed minus x cubed. So you need to maybe go back a little bit and remember some of the stuff you had in Calculus 1. Of course, so x is a function of t. That's the position on the number line. So x prime of t, or dx dt, if you want to write it that way, this is the velocity at time t. Okay, which is kind of hard to read there, but that's the acceleration. Okay, now I'm going to pause this, and if I can, and okay, yeah, we're still going, looks like. Okay, maybe things will look a little easier, a little clearer here, but the second derivative is acceleration. Okay, now what we're after here first is to figure out the velocity. If x equals 1 when t equals 2, so at time t, x is 1, so what's the velocity? Well, the velocity is dx dt, so we'll take, so part A, dx dt evaluated when t is 2 and x is 1 is 2 cubed minus 1 cubed is 7. Okay. So remember, we're talking about a number line here, so if velocity is positive, we're moving to the right here. Okay. Now I've got a graph on the right side, which is the vector field, and in this case, x is kind of up more than positive, but a number line would be thinking about moving to the right here. Okay, so that's the velocity. Next, let's show that the acceleration of the particle is given by the second derivative equals all of that. So we're going to then take the derivative with respect to t of dx dt. Okay, so excuse me. Yeah, and that's going to be the derivative with respect to t of t cubed minus x cubed. So take the derivative of the left and of the right. Okay, so the second derivative with respect to t both times is this down a little bit. Easy, the derivative of t cubed with respect to t is 3t squared. The derivative of x cubed, well, the derivative of the cubed part is 3x squared. But x is a function of t. I don't know the derivative, so the best I can just write is dx dt down for that. And I can substitute in for that because I know dx dt is this thing. So this is 3t squared minus 3x squared times t to the third minus x to the third. And when you multiply all this out, you get exactly what they say we ought to get. 3t squared minus 3x squared t cubed minus 3x, let's see, x squared x cubed, 3x to the fifth. Okay, and that's what they wanted us to get on part B. Can't quite get back to it. Yeah. Okay, so now I have expression for the acceleration at time t. Now, part C, I guess I maybe need a new, probably need a new board here. So let me insert a blank page. This doesn't go away. Okay, so part C. Let's first recall what I've got here. I've got dx dt is t to the third minus x to the third. And in part C, they want us to say, to show that if x equals 2 at time t equals 2.5, okay, we want to then show that we're not going to turn around and get back to x equals 1. So we want to show that, we want to show that particle that's moving along the number line reach the location at any later time. Okay, and the vector field I have, the direction field I have, is going to help us answer the question. But let's look at dx dt. It's t cubed minus x cubed, which factors as t minus x. Difference of cubes factors, in this case, t minus x times t squared plus tx plus x squared. Okay. Now, something I didn't state at the top, but we're talking about a point moving along the number line. So we know, of course, that t is always going to be greater than 0. We're not going to go backwards in time here. And we need to figure out, in order, if this point was going to go back to x equals 1, since it's at x equals 2 now, to reach x equals 1, dt is going to have to be negative, so we're going backwards. Okay. So the question here is, to restate the question is, can dx dt ever be negative, given that we started at this point x equals 2 and t equals 2.5? And of course time can't be negative. Because if dx dt will never be negative, then we're not going to go. I mean, positive dx dt is going to the right, the x's get bigger. Negative would be going to the left. If dx dt is never negative, then we can't go from x equals 2 to x equals 1. Okay. Because we won't ever be going to the left. Okay. So let's analyze this a little bit here. Let me see. I'm going to look at this two different ways, but first, when is dx dt equal to 0? Okay. When is this expression going to be 0? Okay. Well, it's going to be 0 if t minus x is equal to 0. And that second term, t squared plus tx plus x squared, that's never 0. This, when you look at the difference of two cubes, is never equal to 0. So the only place that our dx dt will be equal to 0 is when t is equal to x. So I'm going to draw a little graph here. Here's t, that's time, and here's x. And right along this line, t equals x, we have that the dx dt is equal to 0. Now that's what's called an isocline. I haven't been mentioning isoclines in other problems in this because the book mainly uses those to graph direction fields, and if you've got the program, you don't need to look at isoclines to do a direction field. But anywhere where the derivative is a constant, that's what we call an isocline. Okay, now we are at 2.52. It's not quite drawn to scale. But if this is where dx dt is equal to 0, it's not equal to 0 anyplace else, and this dx dt is a nice polynomial, so it's continuous. It's not going to jump around too much. At this particular spot, when x is 2, when t is 2.5 and x is 2, what is my dx dt? At t equals 2.5, x equals 2, dx dt, well, I don't really care what it is exactly, excuse me. It's positive. Okay. That's the main thing I'm getting at. So dx dt is positive here, over here, not just at that point. It's always positive over here, and it's negative there. I can find it. So we're only going to be traveling backwards. Okay. The only way we could get to x equals 1 is if we were above this line. And we're never going to get above this line, because if dx dt is positive, then that means we're going in the positive x direction. Once we get to this line, if we ever get there, what's going to happen? Dx dt is 0. We're not going to go up anymore. So we're not going to go up into that section. Okay, so that's the point I'm trying to make here, is that since we start going in a positive direction, when we're at 2.52, okay, we're going in a positive direction, and we will not get into will not enter the area where dx dt is negative, which means if I'm at x equals 2 now and the dx dt is never negative, then I'm not going to go backwards to x equals 1, because negative dx dt takes me back. Okay, so what this is kind of algebraically showing that. Let me back up a screen and show you the direction field to give you a little better idea of what's exactly happening when we do this motion. Okay. And these are nice little diagrams. This diagram here, where we've done the positive and negative and the 0 part, is kind of nice. So we're always going up. But if we get to this line where it's 0, dx dt is 0, so we're not going up anymore. So let me back up there. This is using my computer program. I have graphed the which gives you a little different picture than the calculator does, because it draws arrows here. I have graphed the direction field from times 0 to 4, and the x's would go from 0 to 4 as well. And I've located here in the middle is the point at 2.5, 2, and you see a little bit of what the general direction of things look like. They go up, and this line is where the dx dt is 0. These places here where it's horizontal. Okay. Now, so it looks kind of like things go this way, up like that. And I have a better picture. I have kind of zoomed in on, come on, you're supposed to be there. There we go. I have zoomed in on it to show a little better here. I know it says X and Y. This should say T and X. But here's 2.5, 2. Okay, so instead of going from 0 to 4, I now go from 1.5 to 3.5. And you can see that what we would do is the point would go up here and then travel this way. So you won't ever get into the region where the dx dt is negative, where you're going backwards. So the general graphs on these things look like this. If you start on this side, if you start on this side, it's going to look like that. Okay, so that's what I like about these direction fields. We start at this point. Okay, our dx dt are always going to be positive. Okay, let's take a look at a few others. Now, I'm assuming you can have this program in your calculator. This is not from the calculator program. This is from my computer program. But number 10a, I wanted you to sketch the direction field for dy dx equals sine x. This is the direction field for dy dx equals sine y. And I hope you can see that what we've got is solutions to this differential equation. Well, if they're in this region, they're going to look something like this. If they're in this region, they'll look like that, like this, that. So something interesting is happening there and there. Okay. So, do you know what these lines are? Okay. What are the... Well, there are asymptotes, but what's the equations? Look at the function there. It's the sine. These places, there, and it's actually one here. These are all your multiples of pi. So solutions to this differential equation are going to be between 0 and pi, 0 and minus pi, wherever your points are, you're going to have that sort of flow going on there. And if you were actually exactly on 0, dy dx is going to be, well, you'll stay there. There's something kind of interesting here. This y equals 0 and these are very different things here. If you start out at a value close to pi, you're going to go to pi. If you start out at a value close to 0, you're going to go someplace else. So, those are called steady state solutions, but one of them is an attractor and one of them is repels. In other words, if you're close to pi to begin with, you're going to get attracted to pi and stay there. If you're on 0, you're going to stay there, but if you're just a little bit off 0, you're going to go someplace else. So if you're exactly on 0, you're going to stay on 0, but if you're a little bit off, you're going to go away from it. If you're exactly on pi, you'll stay on pi, but if you're a little bit off, you'll go back to it. So it's an attractor. That's getting ahead of things too. But that's a sketch of direction field. dy dx equals sine x doesn't look like this at all. So when you change the variable here, the field is going to be a lot different. Here's another one. Since my computer will draw pretty good pictures, one of the things I might do on a test is give you some direction fields that I've drawn and ask you to interpret them a little bit. And this is what number 18 does. dy dx equals minus y. Okay, and looking at the direction field, so there it is. What can you say about the behavior of a solution as x approaches infinity? Now these little marks are tangent lines or tangent segments to honest to goodness solutions. So there is some solution at that particular spot, and that's its tangent. And you can see that probably what the solution looks like is something like that. Okay. And at this particular point up here, there's a solution that's tangent. This vector is tangent, and it's going to come down. It probably looks something like that. Okay, so draw a few of those curves to see. Actually, this was probably a little too steep. It probably looks more that way. To see what you think it looks like. All right, now, as x approaches infinity, what would you say a solution looks like? Yeah, the solution is y. So no matter where you start, as x approaches infinity, no matter which one of these solutions are, the y's are going to approach 0. It'll get there a little faster if you start over here toward the left, but even so, everywhere it's all going to look like this. So this is actually an exponential function. Okay. And yeah. That finishes that section. Now I want to say a little bit about the next section, even though I'm not going to actually present anything. And what I wanted to do was to just kind of review a little bit of some Calculus 1. And we all come from different places, so it doesn't hurt to review some Calculus 1 idea. Here I've got a function, y equals f of x. I have some point on the graph, x0, y0, and I have the tangent line at that particular spot. So, I've drawn a differentiable function here, so the tangent slope at this particular spot will be f prime of x0. And what is the equation of the tangent line? Okay, well, it's y minus y0 equals the slope times x minus x0. Or y equals f prime of x0 times x minus x0 plus y0. So this is the equation of the tangent line, the red line I've got there. This is what's also called, at least the calculus book I'm looking at here, getting ahead of myself here. The idea here is the tangent line is a good approximation to the function near this point. Okay. x0, y0. So as long as you don't stray too much from the point, the tangent line is close to the function, we can use it as an approximation. Okay, and that's what I mean by, this is sometimes called the linearization of the function f prime of x0, x minus x0 plus y0. Okay. Now, what we're going to want, and I'll go into more detail on this next time when I actually come up with the Euler's approximation formula for a differential equation. But we want to use this idea to approximate a solution to a DE. In other words, we will have a first order differential equation. I should have used a different letter here. Let's let me use a capital F down here because the function I'm using here is not the function up there. The function up there is a solution. I should have used a capital letter for that, but I'm not going to go back and change it. But dy dx will be given by, we'll have some formula in x and y for the derivative, and we'll still have a particular point. Okay, that we know the solution we're after passes through that point. And we'd like to find an honest to goodness solution, but we can't. But what we're going to do is we're going to construct an approximate solution, and we're going to use this idea. Because we know dy dx, then, and if I know a point in a dy dx, I can construct a tangent line that's close to the honest to goodness solution. And I'll go out that tangent line and a little bit, then I'll construct another tangent line, which missed. Okay. And because I've got a formula that'll let me construct tangent lines no matter where I go, and I'll go out that tangent line a little bit. I'll use my derivative formula again. It'll give me a tangent. Okay. I'll go out it a little bit, and I can use my derivative formula again. So what I can do is I can come up with some sort of polynomial approximation. And that's what the next section is, the Euler approximation for a solution to a differential equation. Somewhere, well actually, I know where on my computer I have a program I just don't, that does this, I just can't access it. It was written for a TI-82 and I don't have the connection on my computer that would let me get at it. So anyway, I'm going to try to find a program for, they're really not that hard to write. I could probably write a program for this pretty well. So Euler approximation is going to be based on little tangent line segments, and you get these tangent line segments because that'll give us the slope, and once we have the slope at a particular point, we can construct the next point. We evaluate the slope again, construct the next point, evaluate the slope again, construct the next point. And this will be a pretty good approximation as long as we don't try to go too far. As long as this next point we go to isn't very far away. Okay, that's all we're going to do today. Anybody have any questions? Okay, so Tuesday we'll hit this stuff pretty heavy. I'll have these videos and the boards put on Moodle, but I have to get a YouTube account and a few other things set up before I do that. Okay? Have a nice weekend. Nice long weekend. I'm going to be grading papers and doing other fun things. And it's going to rain so that I can't go fishing. So